Hello and welcome to the next, well, hang on. Uh-oh. Hey Stewie, how you doing? And we're back. Hello. Oh, come on. Son of a... And welcome back to the next video on What the Heck?
Hectogon.
Today's going to be another short video. After this, I will be getting back to the integral videos. I just wanted to kind of keep things moving on this channel. So previously we proved the law of sines, and following from that we did the angle bisector theorem, which is a pretty interesting little fact. Today we're going to cover a similar trigonometric law. It's the law of cosines. There are also laws of tangents and cotangents, none that I know of for secant and cosecant, but we're not going to be covering those because where have you ever seen them? So we're not doing those. Today we're just going to be covering the law of cosines, and if that's not enough for you, suck it. Just kidding. Let's do some math. So let's talk about the law of cosines. So this is just the next trigonometric law. We did the law of sines last time, which related the angles of a triangle to the sides of the triangle. And this is in a similar way going to relate the sides and angles of a triangle together. So imagine I have some triangle where this is some angle theta, here's A, here's B, and here is C. So we have a triangle with two sides A and B, the angle between them theta, and C the opposite. Then it is true that C squared equals A squared plus B squared minus 2 times A times B times the cosine of theta. Okay, this is the law of cosines. So this number squared is equal to this number squared plus this number squared minus 2 times A times B times the cosine of theta. Alright, so this may seem a bit out of left field, but we're going to prove it today. And it's not that difficult of a proof. So I'd have to do it with an arbitrary triangle, which is what I'm going to do, but I'm going to do it specifically in the Cartesian plane, the xy plane. Even though I'm picking a specific position, this is still going to be a general argument, because think about it. Any triangle in the Cartesian plane can be moved physically without changing its shape anywhere in the plane, and it will still be the same triangle, just in a slightly different place. So what I'm going to do without loss of generality is fix one of the vertices of the triangle to the origin of the graph at 0, 0, and fix the other one such that the length A in the previous triangle is laying along the x-axis. So this will be A units in length. So this will be the length A, which means this point is A, comma 0, and this length is A. This length right here. And now I can put the third point anywhere, and that will determine every single possible triangle, because if I put it here, that's one type of triangle, and you can imagine just tracing the third vertex around with the two other sides following it. You can make any triangle you want. And so, again, without loss of generality, I'm just going to put the third one here, right? It doesn't actually matter where we put it. So this is going to be our triangle. So this is A, this side length is going to be B, and this side length is going to be C. I want to find the length of C. How do we do that? Well, first of all, we need to find the two endpoints of C. One of them is A, comma 0, and what's this one? Well, imagine for a second we had a circle with radius B, centered at the origin. So pretend that that semicircle is centered at the origin. Then this circle has radius B, and remember this is some angle theta in here, right? So this angle is theta between A and B, right? And whatever theta is, this is going to have a certain cosine and sine value. And remember, if you recall from why we generalized trigonometry to the unit circle, this line segment with length B is going to have an endpoint with the coordinates B cosine of theta, comma B sine of theta, right? Because that's how trigonometry works in the unit circle. Cosine is the x-coordinate, sine is the y-coordinate, and you simply multiply by the length of the radius. So we have all three coordinates of the corners of the triangle. And so now, to deduce the law of cosines, all we have to do is try and express the length of C, which in terms of the xy plane is actually just the Pythagorean theorem. Because if I drop an auxiliary line here, the height of the triangle, and sort of notate that there, we just have a big right triangle, right? And because it's a right triangle, and C is the hypotenuse of that right triangle, we can simply treat this length a plus whatever this is as the length of the leg of the base of the triangle, and this as the height of the triangle. And then we can do this squared plus this squared equals c squared, because it is a right triangle, and we've proved the Pythagorean theorem a ton of times. All we have to do is figure out what all of these extra lengths are. So we know that that middle point here is the origin, so I don't really need to write that. The length of this triangle is going to be the difference of these two things. So this x-coordinate here is b cosine theta, and the distance between two things is their difference. So the length of the base of this triangle, this new right triangle, remember our original triangle is a, b, c. We've just added these auxiliary lines, where we now know that the length of this is b cosine theta, and the height of this is b sine theta. So the base of the triangle here is going to be from A to b cosine theta. And actually, no matter where b cosine theta is, even if it's on this side of the axis, the distance between two things is just their difference. So this length here is A minus b cosine theta. We have the original triangle with side lengths A, B, and C, which is this obtuse thing here. Remember, it could have been acute, it could have been right, it could have been anything. And I've drawn these auxiliary lines to sort of pad out the triangle so that it's guaranteed to be a right triangle with these extra things here, so I can find out the length of C in terms of its endpoints. And now that we've drawn this diagram, I'm going to write out in a different color so there's no confusion these equations. So we know by the Pythagorean theorem that C squared is equal to the lengths of the legs of the right triangle squared and added together. The length of this is the difference between the two pieces, right? So it's A minus b cosine theta, and it would be minus b cosine theta no matter where that point was, 0, positive, or negative. So it's going to be equal to A minus b cosine theta all squared plus, and then what's this side of the triangle? It's just b sine theta. So b sine theta squared. And all we have to do is FOIL these things out. This will always be equal to c squared, so I'm not going to necessarily rewrite that. And when we FOIL out this binomial, we get a squared minus 2ab cosine theta plus b squared cosine squared theta plus b squared times sine squared of theta, right? And now we can simplify this a bunch, because what can I do? I can rewrite this as a squared, and I can factor b squared out of both of these terms, because they have a factor of b squared, right? b squared times sine squared theta plus cosine squared theta minus 2ab cosine of theta. And now look what happens. What did we learn from our trigonometry lessons? Sine squared plus cosine squared of the same angle is always equal to what? It's always equal to 1, because this is a Pythagorean identity, right? When we generalized trigonometry to the unit circle with radius 1, then the side lengths of those right triangles, given the angle theta, were always cosine of theta and sine of theta, which means sine of theta squared plus cosine of theta squared is always equal to 1 by the Pythagorean theorem. And so this is just 1, which means b squared times this is just b squared. And so we end up with the final statement that c squared equals a squared plus b squared minus 2 times a times b times the cosine of theta. So essentially, if you know any two of the sides of any triangle and the angle between them, you can find the third side using this. And as it turns out, this might look rather familiar in a certain sense, because what if theta is 90 degrees? Well, then we'd have all of this as the same, but then we'd have the cosine of 90 degrees, or pi over 2 radians. And if you recall from doing trigonometry, cosine of pi over 2 radians is 0. So when we have a 90-degree angle in our triangle, thus making it a right triangle, this term goes away. And look what we're left with. A squared plus b squared equals c squared. So really, the law of cosines is a generalization of the Pythagorean theorem. A Pythagorean theorem for all triangles, right? You just have to incorporate some trigonometry, actual trigonometry, instead of basic geometry. Essentially, if theta is 90 degrees, then cosine of theta is 0, and 2 times a times b times cosine of theta is 0. And so we would be left with the Pythagorean theorem, which is exactly what we'd want anyway, because what do we know about right triangles? We know the two legs and the angle between them, which is the right angle, and we want to find the hypotenuse, which means that when the angle is 90 degrees, it should simplify to the Pythagorean theorem, and that's exactly what it does. So there is our law of cosines, and we call that a big fat QED, quote erat demonstratum, I think is what that stands for, which is what was to be demonstrated. Thank you very much for watching, and I will see you in the next video where we will continue those awesome integrals. Goodbye.